Hi friends, Dr. Woroli here. Today we are learning operational amplifiers. The operational amplifier, in short, OPAMP. This is a multi-stage amplifier specially designed to work with many instrumentation application as well as the application where various mathematical operations are implemented. Since it is commonly used with the applications which generates the mathematical operations like addition, subtraction, multiplication, integration, derivative, and so on. And therefore it is called as operational amplifier. The basic symbol and terminals of operational amplifiers is shown in the figure. As we know that operational amplifier is a multi-stage amplifier. It basically consists of four stages. Number of stages are added in any amplifier to increase the gain of the amplifier and overall implementation of the parameter set required for the amplifier. We will see shortly the various characteristics of ideal operational amplifier and the block diagram of ideal operational amplifier. The operational amplifier have two terminals. One is inverting input terminal and another is non-inverting input terminal. And the output terminal. The power supply terminals are shown. One is for positive power supply, another is for negative power supply. Some operational amplifiers can have single power supply also. They are capable of operated with single power supply also. Whereas by default, most of the op-amp are capable of operating with dual power supply and they are basically developed to operate with dual power supply. Now, if you see the symbol, this is a typical symbol of operational amplifier and also the symbol of operational amplifier mu A741. The terminals shown here, pin number 2, inverting input, pin number 3, non-inverting input, and pin number 6, the output. Pin number 7 is VCC plus and pin number 4 is a negative supply VEE. This nomenclature is applicable to the op-amp IC741. Pin number 2 is inverting input, means the signal connected to pin number 2 with respect to pin number 3 is getting inverted and amplified and available at the output. Whereas when the signal is connected to non-inverting input with other terminals grounded, the output is non-inverting, means in phase with the input signal. The op-amp is shown by a triangle symbol and it also indicates the signal flow direction from input to output. The signal is going inside the op-amp from input and the amplified output is available at the output terminal. Normally, single-ended output is shown here. Always output is taken with the output terminal with respect to ground or a reference terminal. Since there are two terminals available, if we apply the input to either of the terminal, that decides what is the operating configuration of op-amp. Here, the following figure indicates what I explained already. See, if the input to the inverting terminal is applied, which is say sinusoidal, then 180-degree phase shifted signal is available at the output. If the input is applied to non-inverting terminal with inverting terminal grounded, the output is in phase. That is the meaning of non-inverting input terminal. Now let us see the powering of operational amplifier. Normally op-amp will be powered with dual power supply. One is positive supply voltage VCC and other is the negative supply VEE. Normally the supply voltage magnitude will be ranging from 9 volt to 24 volt, whereas 12 volt plus minus say plus minus 12 volt and plus minus 15 volt is very common power supply for powering of the op-amp. Here, if you have a dual power supply, you have three terminals. This dual power supply normally consists of a pair of terminal per power supply. One is positive, another is negative. And second power supply again positive and negative. To get the dual power supply from this, you have to make negative of the positive power supply connected to the positive terminal of the lower power supply and connect the common terminal shown here to the ground terminal. Whereas upper terminal now or positive terminal of upper power supply is now plus VCC with respect to ground, and the negative terminal of the lower power supply is minus 15 volt with respect to ground, and that is connected to the power supply terminal of the op-amp. Here, a sample op-amp 741 is taken in consideration. Op-amp can be used as a differential amplifier. We have seen that op-amp have two terminals and therefore according to the application of input, it can be inverting amplifier or it can be non-inverting amplifier or it can be a differential amplifier. In differential amplifier, the inputs are applied to both the input terminals. One input is connected to terminal 1, that is inverting terminal, say V1, and another input V2 is connected to non-inverting terminal. The difference between the voltage V1 and V2 is called as VD, and that is called differential voltage. The output of the op-amp is VO is equal to minus AV into VD, where VD is V1 minus V2 and AV is the voltage gain of the operational amplifier. Here negative sign indicates that the VD is positive at inverting terminal, and that's why output is inverted version of VD. The basic block diagram of operational amplifier is shown in the figure. It is basically a multi-stage amplifier. In the figure, we are observing there are two inputs, inverting input, non-inverting input, and the output terminal here. The various four stages are the input stage, the intermediate or gain stage, third is the level shifting stage, and fourth is the output stage. Input stage is normally dual input balanced output differential amplifier. The differential amplifier is basically a common emitter type of amplifier connected in parallel, or it can be a common source amplifier connected in parallel, and the output of these stages is taken differentially. The details of the differential amplifier circuits are beyond the scope of your subject. But just note that differential amplifier configuration is a configuration where the differential input between inverting and non-inverting terminal is getting amplified and available differentially at the output of the differential amplifier stage, that is input stage. Now, if you want to have higher gain, we have to cascade the number of gain stages, and therefore in operational amplifier also there is additional intermediate stage is implemented, and this is again differential amplifier stage. Normally its configuration is dual input unbalanced output differential amplifier configuration. Now since this amplifier cascading is done with direct coupling, therefore the DC level or quiescent level of the previous stage getting amplified by the next stage, and therefore quiescent level is go on shifting up, which effectively reduces the AC swing of the amplifier, and therefore to restore the swing to maximum level we have to reduce the DC level to 0, and therefore next stage is a level shifter stage. This is normally the emitter follower or source follower type of stage with constant current source. The output stage, now at the output of level shifting stage, the input differential signal is getting amplified to sufficiently high level, but its amplitude, voltage or current can be amplified. But the power level of the signal may not be sufficient. So to increase the power level, normally the final stage of the amplifier, operational amplifier, is a power amplifier stage. So output stage here is a power amplifier stage, which is mostly implemented by using complementary symmetry class AB push-pull amplifier, and it can be implemented using BJT or MOSFETs. This is in short the operational amplifier. We will see the characteristic of operational amplifier in the next topic. The various OPAMP parameters, also called characteristics, are defined as follow. The open loop voltage gain. Now it is a voltage gain term. It is denoted by AVO or AOL. OL suffix stands for open loop, means without any feedback component or feedback component connected externally. This parameter for ideal op amp is infinity, whereas practical implementation of the op amp, the gain of voltage gain of the op amp is very high. AVO, also called AOL or AVD, is very high, and it is defined as the ratio of output voltage to input voltage VO by VD. Second parameter is differential input resistance. It is defined as or denoted as RID or RI. This parameter is also very high for operational amplifier, and RI is defined as RI is equal to VI by II, where VI is the input voltage and II is the input current flowing through the input terminal. The third parameter is the output resistance, denoted by RO, and the output resistance is very low for a practical op amp, and it is defined as RO is equal to VO by IO at VI equal to 0. The operational amplifier from input resistance and output resistance point of view is a perfect voltage amplifier in which input resistance is high and output resistance is low. The another parameter is input offset voltage. It is denoted as VIO or VIOS. It is normally few millivolt. Ideal value for input offset voltage is 0, and it is temperature dependent also. Normally in practical op amp, when no input is applied to any of the input terminals, or we can say that both the input terminals are grounded, ideally speaking, the output of the op-amp should be 0. But in practical op-amps, due to the mismatch in the implementation of internal devices, even though inputs are grounded, output is not 0. This is called as output offset voltage. And this output offset voltage is because of the mismatch in the op-amp. So, the input offset voltage can be defined as the amount of input voltage applied to make the output offset voltage to 0. The output offset voltage is denoted by VOS or VOO, and output offset voltage is present at the output of the op-amp because of the internal device characteristic mismatch. Because still today, the technology is not that accurate to implement the matched characteristic device. There may be few percent or fraction of percent mismatch in the device characteristic, and due to this the output offset is generated. The sixth parameter is input bias current. The current flowing through the input terminal is called as bias current. Since there are two input terminals, there are two input DC currents flowing through the op-amp when both the inputs are grounded. IB1 is flowing through non-inverting terminal, say, and IB2 is flowing through the inverting terminal. The bias current parameter IB is defined as the average value of these two bias currents, IB1 plus IB2 by 2. And these bias currents are also temperature dependent because the internal devices, BJT or MOSFETs, used for differential amplifier stages, those are semiconductor devices and they are having dependent performance. The seventh parameter is input offset current, and it is denoted as IIO or IOS, and it is defined as the magnitude of difference between the two bias current, that is mod of IB1 minus IB2. The next parameter is common mode rejection ratio, and it is denoted by the symbol CMRR. For ideal operational amplifier, CMRR is infinity. Thus, for the practical operational amplifier also, the CMRR is very high. CMRR is defined as the ratio of differential gain to common mode gain. In decibel, the CMRR in decibel is defined as 20 log of AD by AC, where AD is the differential gain and AC is the common mode gain. The ninth parameter is power supply rejection ratio, denoted as PSRR. We have seen in the common source amplifier case, the output also depends on the power supply voltage. But since we assume that the power supply is constant and therefore it doesn't contribute to change in the output voltage due to change in input voltage. Whereas all practical power supply voltages are not constant. They are varying slightly. And due to that, when these practical power supplies are used for powering the operational amplifiers also, if the power supply varies, even though it is varying very slightly, the output of the op-amp is going to change. No doubt it is change in fraction of millivolt. but the change is there, and that will be qualitatively mentioned by the parameter power supply rejection ratio. Power supply rejection ratio is defined as the ratio of change in input offset voltage due to change in power supply Vs. In decibel, it is 20 log of delta VIO by delta Vs. Now let us summarize and compare the ideal op-amp parameters and practical op-amp parameters. The first circuit diagram shows the equivalent circuit of a practical op-amp, or in general the operational amplifier. Ri indicates the input resistance between the two input terminals. Ro represents the output resistance looking inside the output terminal, whereas AV into VD is the amplified output voltage by the amplifier, where AV is the voltage gain and VD is the differential input voltage. For ideal operational amplifier, Ri is infinity, Ro is 0, AV is infinity. When AV is infinity, which means that differential input voltage is 0. And differential input voltage is nothing but difference between the two input terminal voltage V1 and V2. So V2 minus V1 is the differential input voltage, or it can be defined as V1 minus V2. Only sign will be changed. So therefore, in the table, the ideal values of the ideal characteristic of op-amp shown here. Input resistance Ri equal to infinity, output resistance Ro equal to 0, voltage gain is infinity. The bandwidth provided by the ideal operational amplifier BW equal to infinity. The common mode rejection ratio is infinity. The slew rate is infinity. The input offset voltage or total offsets in the operational amplifier, which is considered to be ideal is ideal is 0. The power supply rejection ratio is 0. The practical op-amp characteristics, also called as op-amp parameters. A typical op-amp IC741, which is very commonly used in the commercial circuits, is taken for consideration. The input resistance Ri for IC741 is 2 mega ohm. Ideal value we know it is infinity, but 2 mega ohm is significantly high. Output resistance Ro here is 75 ohm. The voltage gain of the 741 op amp is 2 into 10 raised to 5, which is very high. Bandwidth of the operational amplifier 741 is up to 1 megahertz. Common mode rejection ratio is 90 dB. The slew rate denoted by S is zero point 0.5 volts per microsecond. Input offset voltage VIO S is 2 millivolt. Power supply rejection ratio is 150 microvolt per volt. The input bias current IB is 50 nanoampere and input offset current is 6 nanoampere. So if we compare the practical value and ideal values, the practical op-amp characteristics are approaching towards the ideal values. More and more closer characteristics of practical op-amp to ideal op-amp indicates the best quality of operational amplifier. Let us see a simple application of op-amp. Op-amp open loop differential voltage amplifier. Op-amp normally not used in the open loop configuration as an amplifier because it is very sensitive since the gain of the operational amplifier is very high. and therefore some sort of negative feedback is always recommended to control the gain to the stable value. But since we are considering the open loop configuration, let us see how the differential amplifier can be implemented using OPAMP. Say one input V1 is connected to non-inverting terminal and second input AC input is connected to inverting terminal. The difference between the two input voltages V1 minus V2 is nothing but the differential input voltage, and the output is taken at the output terminal. This differential voltage Vd is amplified by the open loop gain or voltage gain of the amplifier, and therefore output voltage is AV into Vd, that is mentioned in this equation. VO is equal to AVOL into Vd. Whereas the practical operational amplifier, there exist the two types of input voltage due to mismatch in the op-amp. One is the differential voltage that we know, that is the difference between the two input voltages. Whereas due to mismatch, there is a common mode signal generated, and that also acts as an input and contributes to output. And therefore, output voltage of the practical op-amp is defined by the equation VO is equal to AVOL into VD plus AVC into VC. This AVC is the common mode voltage gain. For practical operational amplifier, even though this value of AVC is very small, and therefore contribution of common mode voltage gain, and that is nothing but mismatch, is very small. Most of the cases we are ignoring it, and therefore we are using the ideal expression VO is equal to AVOL into VD. Since AVC into VC is very small and negligible in most of the practical cases. The maximum output available from operational amplifier is limited by the supply voltage. If the supply voltage is plus Vs and minus Vs, then maximum output voltage denoted by VO sat plus or VO sat minus, and that is approaching to the positive and negative supply voltage respectively. Whereas in practical operational amplifier, the saturation output voltage is slightly less than the supply voltage. For example, if the supply voltage is plus 15 volt, then maximum output voltage VO sat positive is limited to 13 to 14 volt. And so is the case with negative power supply, that is limited to minus 13 to minus 14 volt when minus 15 volt negative power supply is used. The operational amplifier in practice is mostly used in the closed loop configurations. The three primary configurations exist for operational amplifier: inverting amplifier, non-inverting amplifier, and differential amplifier. Whereas voltage follower is a extension of non-inverting amplifier, that is also called as unity gain buffer amplifier. Let us see the inverting on amplifier configuration. In this case, the feedback components R1 and R2 are connected across the operational amplifier inverting terminal and the input voltage. Here input is fed to inverting terminal via resistance R1, and the resistance RF is connected from inverting terminal to the output terminal. Now in this case, with the non-inverting terminal, that is voltage V1, that is grounded, means it is 0. There is a concept of virtual ground exists in this operational amplifier configuration. Now, what is virtual ground concept? We know when the op-amp is powered with the power supplies with finite values, say plus 15 and minus 15 volt, we know that in operational amplifier, maximum output voltage is limited to the supply voltage, means it is finite. Ideally speaking, the op-amp have infinite gain. So finite output divided by infinite gain is the input voltage, and that tends to be zero. And therefore, when V1 is grounded, due to feedback components effect or negative feedback provided by the feedback circuit, the op-amp output keeps the inverting terminal at the same potential of non-inverting terminal, so that the effective difference between inverting and non-inverting terminal voltage equal to zero. Since non-inverting terminal is connected to ground and voltage of inverting terminal is also same as zero, that is nothing but the ground voltage. Therefore, we call the inverting terminal is at ground potential, but not actually connected to ground. It is virtually brought to the ground. And therefore, the concept is that the virtual ground will be created at inverting terminal due to feedback component, which provides the negative feedback and maintain the inverting terminal at ground potential virtually. So therefore, in this circuit, when V voltage V1 is 0, ultimately V2 voltage V2 at inverting terminal is also 0. Now when input voltage Vin is applied, let us see the operation for the complete half cycle. During positive half cycle, since it is the inverting amplifier, when input is increasing in positive half cycle, the output is decreasing in the negative direction. During negative half cycle of the input, that is the hatch portion from pi to 2 pi, input is decreasing in the negative direction and therefore output is changing in the positive direction from pi to 2 pi. Whereas the amplitude of output is larger than the amplitude of input by the amount that is called as voltage gain. Now, what is the voltage gain of the circuit? Now, let us analyze the circuit and find out the analytical expression for voltage gain. In the circuit, let us see here, input voltage is connected between this point with respect to ground. Whereas V1 is at ground, therefore, due to virtual ground concept, V2 is also at the ground potential. And therefore, effectively, input voltage Vin is appearing across R1. So therefore, voltage across R1 is VR1 equal to Vin, that is written here. And this is because of the virtual ground concept. So Vn is equal to I1 into R1. This is Ohm's law. Current flowing through the resistance into the resistance value. That is nothing but the input voltage. Here, when this current comes to the terminal of the op-amp, since we know that the input impedance of the operational amplifier is infinity or very high, therefore, the current going through the input terminal of the op-amp is ideally zero. Therefore, whatever the current I1 comes through R1, that leaks through the resistance RF to the output terminal, and that is denoted here as IF. Since the input current I in of the op-amp terminal is 0, therefore IF is same as I1. From these two equations, we will substitute the value of I1 in equation number 1. Also, we have a third equation. The output voltage VO from the figure. See, this is a VO terminal, which is with respect to the ground terminal here, right? Whereas this ground terminal and the inverting terminal is at same potential. Therefore, VO is effectively appear across RF with output terminal negative and common terminal positive. Therefore, we can write that VO is nothing but voltage drop across RF. Since current through RF is IF, therefore we can write VO is equal to minus IF into RF. Since we have the values of IF and V in from equation 1 and 2 here, we will just substitute the value of IF equal to I1 is equal to V in by R1 in the equation of VO. And therefore VO is equal to minus V in by R1 into RF. Taking V in on left hand side, and therefore voltage gain AV is equal to ratio of VO by V in, and that is equal to minus IF by RF by, that is equal to minus RF by R1. So we can say from this equation, when the op-amp is used with negative feedback, the gain of the op-amp simply controlled by two external feedback resistance component, and therefore it is very easy to set the gain of the op-amp by choosing the appropriate value of the resistance. The next parameter is the input resistance, and we know it is defined as V in by I in. Here I in is nothing but the current flowing through the input terminal or input resistance, that is I1, and therefore in inverting configuration Ri is equal to V in by I1, whereas from equation of I1, this first equation, I1 is V in by R1. So therefore substitute in here in this equation Ri is equal to V in divided by V in by R1, and that is therefore equal to R1. So ultimately the input resistance of this configuration is same as the external resistance connected between the external source to the inverting terminal. Since this resistance is normally of less value in the range of few kilo ohms, therefore inverting configuration input impedance is less. The output impedance of the circuit now. It is the impedance looking inside the output terminal of the operational amplifier with respect to ground. And it is defined as the ratio of VO by IO when V in equal to 0. And if you remember the equivalent circuit of the op-amp, there a small arrow, let us go back and see here. The output resistance is shown. So when both the inputs are connected to 0, that is V in equal to 0, this VD is 0, therefore AV into VD is 0, therefore RO is effectively coming across the output terminals. And therefore looking inside the output terminals, the effective output impedance is RO. Let us go back. So RO is approaching to 0 since the op-amp is ideal. For practical operational amplifier, the value of RO is very low. For op-amp 741, the output impedance is just 75 ohm. And with negative feedback, it will further reduce by the desensitivity factor, which is the factor by which the gain will be reduced, and that is 1 plus A beta. We are not going in detail of the desensitivity factor, but further negative feedback reduces the output impedance towards the ideal op-amp output impedance, and therefore output impedance of the practical configuration also approaching to zero. The another configuration now, non-inverting configuration of the amplifier. Now the name itself indicate that we are now connecting the input to non-inverting terminal. See here, Vin is connected to non-inverting terminal, and R1 and R2 as usual the feedback resistance, whereas the another end of R1 is grounded. Now in this case, when V1 is applied to the non-inverting terminal, the gain of the feedback amplifier is limited by the external components RF and R1. Let us say it is AV. So therefore output voltage is AV times V in. What is the value of AV that we can analyze and find out the expression further? Okay. So when input voltage is applied here sinusoidally, let us see during positive half cycle, since it is a non-inverting amplifier, output is also increasing sinusoidally in positive half cycle in the positive direction. When input decreases in the negative half cycle in negative direction, the output also decreases in the negative direction and constitute the amplified version of the input negative half cycle. So we will see that output voltage is in phase with the input voltage, and that's why the configuration is called as non-inverting configuration. We will observe that the amplitude of output voltage is larger than the input voltage, means output voltage waveform is the amplified version of the input voltage waveform. But how much amplification this configuration provides? For that purpose, we have to analyze the circuit and find the expression for voltage gain. In this circuit, we have V2 is same as V in. The reason, since op-amp is having infinite gain and output is always finite when the finite supply is applied. Therefore, differential voltage exists between the two input terminal is finite output divided by infinite gain of the op-amp, that is equal to 0. And therefore, the input differential voltage between the inverting and non-inverting terminal is 0. And therefore, when non-inverting terminal is at potential V in, therefore, inverting terminal also comes at the same potential. And this is because the feedback effect provided by R1 and R2. Indirectly, we can say the component R1 and R2 tries to keep the inverting terminal at the same potential of non-inverting terminal. In this case, non-inverting terminal is kept at V in, and therefore inverting terminal is also coming at the same voltage, and therefore we have written V2 is equal to V in. Whereas V2 can be obtained from the resistance divider. There was a mistake in the typo mistake in the file, therefore I have corrected it and I have changed the file and reloaded. So let us see now. The voltage V2 is same as V in, and that is nothing but voltage across R1. So voltage across R1 is nothing but R1 upon R1 plus RF into VO. Taking VO on left hand side and other terms at on right hand side. And therefore we are getting VO is equal to 1 plus RF by R1 into V1. Sorry, V in. And therefore, taking V in on left hand side, we can get the expression for voltage gain AV of non-inverting configuration, that is VO by V in is equal to 1 plus RF by R1. From this expression, again we conclude that the gain of the amplifier is simply set by the two external resistance. And this is possible because the idealness of the operational amplifier. Also, this equation tells us that gain is positive. So, therefore, output is in phase with input. And the total amplification provided is equal to 1 plus Rf by R1. Again, third observation is the gain is always greater than 1. The second parameter, input resistance. As usual, it is defined as the ratio of input voltage to input current. Since the input current, now input is applied to non-inverting terminal. Since op-amp has very high input resistance between inverting and non-inverting terminal, and therefore, ideally, no current flows through the input terminal of the op-amp. And therefore, I in the non-inverting terminal is approaching to 0. And therefore, the ratio V in by I1, that is I in, is equal to V in by 0 approaching to infinity. The output resistance, as usual, RO is defined as VO by IO when V in equal to 0. From equivalent circuit, when V in equal to 0, the output circuit of the op-amp effectively reduced to the output resistance RO from the equivalent circuit shown. And that is I for the ideal operational amplifier approaching to 0. Whereas for practical operational amplifier, this value is very, very small. And with negative feedback provided by R1 and R2, it is further reduced to very low value and nearly approaching to 0. And therefore, output resistance of non-inverting amplifier with feedback is approximately 0. Now, the third application, which is just an extension of non-inverting amplifier, that is called as unity gain voltage follower or unity gain buffer. We have just derived the voltage gain AV of the operational amplifier in non-inverting configuration. So here the circuit shown is a non-inverting configuration. Compare it to non-inverting configuration. In non-inverting configuration, if RF is set to 0 means short circuit and R1 is open circuited, then this configuration results. Means output terminal is directly connected and feedback the output voltage directly to the inverting terminal. And input is as usual applied to the non-inverting terminal. Since input is applied to non-inverting terminal, this is a non-inverting amplifier. Now gain of the amplifier in non-inverting mode is AV is equal to 1 plus RF by R1. We have just derived. Here the value of RF, see here value of RF is 0 and value of R1 is infinity. So RF by R1 ratio effectively comes out to be 0 and therefore total voltage gain of the circuit is approaching towards 1. Means output is just the same version of the input, means output follows the input. Output is in phase with the input with the same amplitude and therefore this circuit is also called as voltage follower or unity gain buffer. That's all about the theory of the operational amplifier. Let us have some examples, simple examples. In an operational amplifier, which is used in non-inverting mode, with R1 equal to 1K and RF is equal to 10K with the supply voltage plus or minus 12 volt. And you are asked to calculate the output voltage for following inputs. One, when input is 100 millivolt and when input is 5 volt. It is a non-inverting configuration. So what is given we are writing here. R1 is 1K, RF is 10K, input is 100 millivolt first case and input is 5 volt the second case. So let us first calculate the gain of the amplifier. You have to draw the circuit and refer the circuit back of the non-inverting amplifier. We have just derived the expression voltage gain with feedback AVF is equal to 1 plus RF by R1. Therefore, AVF comes out to be 1 plus 10 by 1, that is 11. So, when input is 100 millivolt, output is AVF into Vin, that is 11 into 100 millivolt. So, 1100 millivolt, that is 1.1 volt. So, we have calculated the output voltage for input equal to 100 millivolt. Let us see and calculate the output voltage for Vin equal to 5 volt. So, just substitute the value of Vin here. VO is equal to AVF into Vin. So 11 into Vin, that is 5 volt, that comes out to be 55 volt. But output, we know output voltage VO cannot be higher than the positive supply voltage or negative supply voltage. We know in OPAMP the output is bound by the positive and negative supply voltage to the maximum level. Here the maximum supply voltage given is 12 volt, and therefore in positive direction maximum output voltage will be stuck at 12 volt, and therefore here theoretically when we calculate the output voltage is 55, means op-amp output try to increase the value and saturates at the supply voltage and output voltage remains equal to 12 volt. We are saying that this amplifier saturates when the input voltage applied is 5 volt. Another example is on inverting amplifier. The resistance values are given R1 1K, RAF 15K, supply voltage plus or minus 15 volt. Vin is 150 millivolt and second value of Vin is 2 volt, and you have to calculate the output voltage for these two different inputs. Similar problem we have seen for non-inverting amplifier. Here configuration given is inverting configuration, and we know the voltage gain AVF is minus RF by R1. So that comes out to be minus 15. Now output voltage is gain times the input voltage, that is AVF into Vin. Substitute the value, we are getting the output voltage minus 2.25 volt for the input of 150 millivolt. Now when the input voltage is 2 volt, let us calculate the output voltage. Substituting the value of input voltage, that is AVF into Vin, that is minus 15 into 2, that is minus 30 volt. Again, we know that maximum output voltage is limited to plus or minus saturation voltage of the output, and that is limited by the supplied power supply. Here maximum supply given is 15 volt, and therefore output voltage is stuck to minus 15 volt here. Whereas in case of practical operational amplifier like 741, the maximum saturation output voltage is limited and not even up to the supply voltage. It is only 90% of the supply voltage. Exactly speaking, for 741 at 15 voltage, the maximum output swing will be plus minus 13 volt. And therefore, approximately 90% of the supply voltage is 13.5. And therefore, output will saturate it to minus 13.5 volt in practical case. Whereas if you consider the op-amp ideal, then we can say that maximum output voltage is equal to the negative supply voltage minus VEE, that is minus 15 volt. That's all, friends. So we have finished the operational amplifier. That is the last topic of unit number 2. So we will stop here. Bye bye.